few slides that we did not explain. And then we're going to explain how semaphore works in Xenu. And then if we have more time, we're going to talk about how interrupts work in Xenu. Okay. All right. So in process creation and termination, there's a few slides about resumption, right? So we talked about how to suspend a process, but we did not finish how to resume a process. Okay, we're going to finish that first. Yeah, so again, let's start with the overview. We have a process and it can go through these life stages. So far we have learned these 3 life stages. The process can be ready, the process can be current, the process can be suspended. So if the process is current, it means that it's running on the CPU. And in Xenu, there's only one CPU, right? So there's only one process that can be current in Xenu. And ready means that this process is in the ready list. And if it's in the ready list, it means that when resched is invoked, it can be considered to be switched in through context switch. Okay. So there is a ready list that has all the processes that are ready to be switched in. And suspending. Right? So when the process is suspended through the suspend system call, right? It's put in this state, suspended. And it can be resumed through the resume system call. Okay? And today we're going to finish talking about the resume system call. We jumped ahead to talk about multi-level feedback queue, but now we need to come back finish this part. We talked about this template for system calls. Okay, let's quickly go through how suspend is implemented again, just to refresh everyone's memory. Right? This is a suspend system call. You can use it to suspend one process using the process ID as the parameter. Right? And the beginning of this function is very standard. Right? So you use a mask to disable the interrupt, and then you check whether the arguments are correct or not. Okay. So, then you using the argument, the process ID, you get its process entry in the process table, right? And then you also check error, and once you check pass this checking, then you handle suspend using 2 branches. If the process state is ready, that's very simple. If the process state is ready, it means that this process is in the ready queue, in the ready list. It's not running currently. So it's very easy. You use this get item to remove it from the ready list, and then you set its state to be suspended. The process is not running, so you don't need to do anything. Okay, the process is in ready list. It means that the execution context of that process has already been stored. Right? So there's nothing that you need to do here. Else, this means that the process state is running. Right? It's current. If it's current, it means that you need to, of course, still set its state to suspended, and then you call resched. Right, for 2 purposes, right? One is that because this process is currently running, you want to, and you are suspending it, so you need to switch it out and switch in another ready process. Right? And second, this resched also saves the state of the current running process. Okay. Right. So then you call suspend system call. This is the main logic of a suspend system call. The others are just checks, right? Checking for errors. But these two branches are the main logic. Okay. All right. So is call reschedule to schedule itself out. Now the remaining part of this code, when is it executed? And how does this remaining part of the function, suspend function, get executed?
It will be executed by the process that's context switch A.
After context switch, and also something else. Right? This process is suspended. No one can context switch it in. Right? This is a suspended process. It's removed from the ready list. No one can suspend. No one can switch it in. So there's something else that needs to happen for this context switch to be enabled. Right? But I'm just pointing this out, right? So that's already a good answer because we haven't learned that yet. But just this gap is filled by resume system call. Right? So that's the functionality of resume. Because this process is suspended, it's removed out of that ready list. So before it can get switched in, someone else needs to put it back to the ready list. Right? That's the whole purpose of resume. When you call resume, you're going to change this process state from suspended to a ready process and add it into the ready list. So it becomes a normal process again. And then in the future, when reschedule is invoked, context switch happens, then you come back to this process and finish the remaining of this function. Okay, but that's this is just leads to why we need to resume. So, because once you call suspend, it's out of the ready list. So normal context switch will not be able to resume this process. You have to have a special resume system call, and that reverts this effect of a suspend system call. Okay. All right. So process resumption. Right. So that's what we need. The idea is that we need to resume the execution of previously suspended process. Right. So some detailed resume returns a priority of the resume process. Okay. Right. So the goal is that you want to make the process eligible to use the processor again, because suspend system call removed the process out of the ready queue and mark its state as suspended, so it's not eligible for using CPU. You need to revert this effect, right? And reestablish the scheduling environment. Okay. So what does this mean? Why do we need to reestablish the scheduling environment? The scheduling environment, just to remind everyone, it says that at any moment in during the execution, the process that has highest priority should be running on the CPU. Right. So suspend changes this. Right? When you suspend the process, this process might be the one that has highest priority. Right? So you change its state to suspended and move it out of the ready queue. So this process that has a highest priority will not be able to run on the CPU. Right? So when you resume this process, you need to make sure that the scheduling environment is respected. Which means that when this process that has higher higher priority is resumed, you need to use context switch to switch it back and make it run on CPU. Okay, that's why you need to reestablish a scheduling environment here, and this is actually done very simply, right? So which we'll see later. Okay. So the general steps. You move the suspended process back into the ready list, and of course change the state from suspended to ready and call reschedule. Reschedule always reestablish the scheduling environment, right? Because it picks the one process that has highest priority and put it onto the CPU. Okay. Okay. Yeah. So resume does not guarantee instantaneous execution of the resumed process. Right? If this process does not have highest priority, it stays in the ready queue. Right. Okay. So how to move a process to the ready list? Okay. So now we'll see a few functions that Xenu relies on internally, and they might not be exposed to the user application like other system calls, but they are reused by other Xenu OS kernel functions. So they are still important functions. Okay. So yeah, so this one is called ready, right? Xenu includes an internal function named ready that makes a process ready. This ready takes a process ID as an argument, right? It's going to make this process ready, and then inside the ready, it changes the process state to ready, and then insert the process onto the ready list, and ensure the scheduling environment is enforced. Implementation is still very straightforward. Right? Okay, this is the ready functions implementation. Right? It takes a PID as a parameter, and what it does, the main logic is really here, right? So it gets the process table entry and changes its state to be ready, and then insert this process into the ready list. Right? Remember, the ready list is ordered by the priority. Okay, and it calls reschedule. Right? Well, why does it call reschedule here? Right, maintain the environment. In case this process is inserted into the ready list has the highest priority, right? You need to call reschedule to schedule it in to replace the current running process. Okay. Right. So whenever you insert something into the ready list, you almost always want to call this reschedule if you don't know the priority of these items. Right? Okay. Right. If the inserted process does not have the highest priority, it doesn't matter. Right? It won't affect anything. Right. So this is a ready function. Yeah. So this is to explain, right? So how this ready function enforce the scheduling environment through invoking reschedule. Okay. Yeah. So that's the more detailed explanation, but we won't read through these slides anymore. If you're interested, you can read it offline. Okay. All right, now resume. Right, once we have ready function, resume is very easy to implement. Right? So resume takes this PID as a parameter, and these are all normal setup and checking, and the core logic is just here. Right. Once you get the process from the process table, right, and you just call this ready. Okay, that's it. Inside the ready, remember, it inserts the process back into the ready queue and changes the process's state to be ready and call reschedule. Right? Everything actually happens inside the ready function. Okay. The ready function, why is it implemented as a separate function? So later you will see, right, this ready function will also be reused by some other system calls. Okay. Right, so this is resume and ready. Okay. Right, so we also talked about this briefly in our previous lecture. The ready processes, they are kept in a queue, the ready queue, the ready list. But the suspended process are not placed on any queue or any list. Okay. What is the reason? Okay. So the reason is explained here. Right? Because the function that resumes a process always requires the caller to supply an argument, which is a PID, which means that whoever wants to resume a process have to know the PID directly. Okay, so so this requirement means that the caller of resume need to know the PID, and internally inside among the suspended process, you do not need to maintain a list of them, because the application who calls resume knows the PID. Okay. Right. So the consequence is that there is no reason to keep a list of suspended processes, right? Because the application knows the PID of these suspended processes. Right? Okay. Yeah. So in general, an OS only places a process on a list if a function needs to handle an entire set of processes that are in a given state. Okay. For example, the scheduler needs to find the highest priority ready process to do context switch. Right? That's why the ready processes are put in the list. But among the suspended processes, there's nothing. Right? There's nothing that you do for the entire set of suspended processes. The only functionality that manipulates these suspended processes are resuming them one by one, specifically picked by the application. The application directly picks which process to resume. Yeah, so there's no function that handles the entire set of suspended process, so you avoid any list. Right? So this is again reflecting the design principle that you want to follow when you implement any complicated software. You want to minimize anything that you add into your software system. Right? In this case, you might think, okay, ready processes are in a queue. Why don't we just put all the suspended processes in a queue, just in case, right? Just in case. But right, so here you can see that the design of Xenu follows this principle closely. Right? When you don't see there's a need, right, to implement the queue for suspended process, then you don't do it. Any so-called premature optimization can easily become a debt, a technical debt, in later development. Okay. Right. So the Xenu OS is not too complicated, but these lessons will carry over to other complicated software systems, which we will work on in the future. And also, even I think right now, because people are relying more and more on AI and the language model, right, to do programming, which is a trend that we all have to admit. But this ability to examine the quality of the code generated by language model and AI, right? So you still need to have that in order to work on complicated software. Otherwise, the code that the AI generates to you is just a bunch of code that you don't know how it works. You don't know the quality of the code. It will be very hard to maintain. Okay. Yeah. So if you want, if I'm going to see what is the takeaway from this course, that I hope students have right after taking this course, I hope it's design principles, right, for complicated software. So that will a specific knowledge that about OS, about locking, semaphore implementation. Right? So these are useful, but it also depends on in the future what you are going to work on. Right? What is the specific type of system you're going to work on. But the design principles, right, how to minimize the complexity and design the system in an elegant way. Right? This, if you can learn these lessons from Linux design, they will carry a much longer way than the other specific knowledge to learn. Okay. Right. So this is another good example, right? So you know exactly under what scenario you need a queue or a list for a set of processes, and because suspended processes do not fit this this categorization. You don't have any function that will analyze the entire set of suspended processes, so you don't need a queue. You don't need a list for suspended processes. Okay? Right, hopefully this makes sense. Yeah, so this is the missing part. Okay, yeah, this is the missing part that we jumped ahead, right? So how to resume a process. We talked about the suspending a process, resume a process, create a process, terminate the process, and also context switch, right? So the major part of the process lifecycle we have already covered. All right, now let's move on to semaphore. So this lecture, hopefully we can finish talking about semaphore. All right. So coordination and synchronization. I think the takeaway is that the high level idea is that in 252 you learn how to use semaphore to solve concurrency issues like data race. But now in this course, in this lecture, hopefully you will learn how to implement semaphore. Right? So how to implement this mechanism that we use, synchronization mechanism that we use to solve concurrency issues. All right, so jumping out of the technical details, right? So why do we need to even worry about synchronization mechanisms? Why do we even talk about them? Why did they become a hot research topic? Right? Even nowadays, in the cloud environment, synchronization or lock-free programming, wait-free programming is still a hot topic. And it impacts the performance of cloud system by a lot. Right? When we implement distributed transactions in a large cloud system, their performance is highly impacted by this synchronization mechanism that they use in the cloud system. Okay. So, right. So the underlying reason, right? So if we link it back to the history of OS, remember the past months we have been learning about processes, and the whole point of process is to enable concurrent execution of programs, or time-sharing execution of programs, right? So you have an OS that fixes that you have multiple programs running concurrently in your computer, right? And this is where the issue arrives. Right? There's a good reason for that, right? So when you have multiple processes running concurrently in your OS, you can alternate between them. And some of them can be using the CPU, some of them can be using the I/O, so they are more efficient. But also because of this, right, because you have multiple processes running concurrently in your OS, that's how the concurrency issues, the data race, those issues arise. So people developed time sharing, concurrent or multi-programming OS for performance improvement, but because of these concurrency issue arise, and then we need to figure out a way to address these concurrency issues. And all the synchronization mechanisms are designed for this purpose, right, to address the concurrency issues that arise from multi-programming or concurrent execution. All right, so yeah, so the coordination of processes, right? So this is talking about the synchronization. Right? So we are using the synchronization mechanisms to coordinate processes so that we can avoid concurrency issues. Right? So they are necessary in a concurrent system. Right? They avoid conflicts with multiple processes access shared items, and they allow a set of processes to cooperate in a way that appears as they are not affecting each other to the external observer. Okay. They can also be used when a process waits for I/O or a process waits for another process. Right? An example of cooperation among processes is Unix pipes. Okay. So later we'll see. Actually, let's use this jump ahead a little bit, right? So wait for I/O. So in 252, everyone should have learned how to use a semaphore to protect a shared variable. Right? But and it's very simple, right? So you before you enter the critical section, you call wait, right, to use on that semaphore, and after you leave that critical region, you call signal. Right? You are using the semaphore like a mutex, essentially. Okay. Now consider I/O. Right? How do you use a semaphore to do I/O? That's actually how Xenu uses performs I/O, right? Xenu really just use semaphore to perform I/O. How does Xenu use semaphore to do I/O? Anyone has read the code and understands? For example, when protecting a shared variable, suppose when you're using semaphore to protect a shared variable access, what do you initialize this semaphore to? Right? What's the initial value that you assign to it? Yes?
I didn't read the Xenu source code, but I assume if you had like for one network card, for example, you would start it with a semaphore. Maybe like you can only have one device, so only one thread can utilize the network card at once.
That's a good try. That's a good try. Yeah. So that idea protects, ensures okay, only one process can use the device. So there's no multiplexing. Xenu uses it slightly differently. Let's take this step by step. Right. So when you protect a shared variable access using a semaphore, you initialize the semaphore's value to be 1, which means that there's only one process that's able to access that shared variable, enter the critical region, and access the shared variable. Okay. When the process performs I/O, what do you think it initializes the semaphore's value to? Right? It also calls wait. It will call wait. For example, when it's doing I/O, it will call wait. What does it initialize this semaphore's value to? Does it initialize to be 1? So maybe we'll reach there later, right? So I'll explain at high level what it does. So using semaphore to do I/O is very different. You initialize the value to be 0, and when you start doing I/O, when the process starts doing I/O, it will call wait on the semaphore, which means that it directly puts itself into the semaphore queue, right? Because it wants to wait for the I/O to finish. Okay, and then when the I/O finishes, the interrupt will call signal. When the I/O finishes, the device will trigger the hardware interrupt, and in the interrupt handler, it will signal this semaphore, and the process who's waiting in this semaphore's queue will be notified and will be waken up because its I/O has finished, and then when it's waken up, it can continue execution. It's very different from how semaphores are used to protect a shared variable access. Right? All right, so then we'll reach there, right? So we'll see how it's used to protect I/O. Okay. Yeah. Process coordination mechanism handle two basic situations: producer-consumer interaction and mutual exclusion, right? So which you have learned in 2x2. Okay. Right. So producer-consumer synchronization, which is the I/O, which is a pattern that fits the using semaphore to perform I/O. That's usage scenario. Okay. So in this scenario, there is a first in first out buffer shared by multiple processes. And the process that deposit items into the buffer are the producers, and processes that are extracting items from the buffer are called consumers. Okay. The programmer must guarantee when the buffer is full, a producer will block until the space is available. The producer cannot keep feeding items into the queue, into the buffer. And when the buffer is empty, a consumer will block until an item becomes available, right? Be deposited into the buffer. Okay. A given process may act as a consumer for one buffer and a producer for another. Right? So in Unix pipeline, a process may read input from one pipe and write output to another. Right? The second scenario is mutual exclusion. Right? In a concurrent system, you have multiple processes accessing some shared variable, and you want to make sure that there is no data risk. Okay. Right. So we use the term atomic to refer to an operation that is indivisible. Right? So the hardware performs the operation in a single instruction that cannot be interrupted. Right? So there are some hardware instructions that guarantee this, and so all of the synchronization mechanisms rely on hardware primitives. Right? These kind of hardware primitives, atomic operations. Many data operations are not atomic, right, which means that a sequence of multiple operations are used to change a data item. Okay. And the programmers must take steps to ensure that when one process executes a sequence of operations to change a data item, and no other process can attempt to change concurrently. Okay. One example is that some trivial change, like x plus plus incrementing x, can require a sequence of hardware operations. Right? So x plus plus, this increment, what is the sequence of operation from this one single line of C code? If you're familiar with C, you probably know this, right? So incrementing x, in fact, it involves a sequence of operations, not just one operation.
Load, add, and then store.
Right. You first load x value from memory into the register, right? and you do increment. The next instruction is that you increment this value in the register, add 1 to it. And then you store back. You store this register's value back to memory. There are multiple steps, even in this single line of C code. Okay. Right. So to prevent the data risk, a programmer must ensure that only one process accesses a shared item at any time. Right? The general approach, right? Once a process obtains access, make all the other processes wait. Right? And when the process finishes accessing the item, grant access to one of the waiting processes. There are 3 techniques that allow us to do this do this general solution. One is a hardware interruption, right? So we can disable interrupts, which means that when you disable interrupts, there's no concurrent processing. Right? When you disable interrupts, there's no timer interrupt, there's no context switch. So your process is going to hold the CPU forever. Of course, in a single CPU scenario, in a multi-core CPU, the story is different. In a single core CPU, if you disable interrupt, your problem is solved. There's only one process executing at one point in time, no concurrent processing. Okay? So another technique is spin lock. All right? Spin lock, which means that, actually, let me leave this as a question. The other is a semaphore. What is the difference between spin lock and semaphore? There are many subtle differences, but at high level, what is a high level difference between them? Yes?
Is it just like a spin lock with busy waiting?
That's business base, right? What does semaphore do differently?
I think it waits for instructions.
It waits, right? So when the difference is that when you use semaphore, when the process waiting on the semaphore, it does not use the CPU. It puts itself in the wait state and schedule itself out, right? Or put itself to sleep. In different OS, it might be implemented differently, right? Then the spin lock is different. If you use spin lock, your process is still running continuously. There's no other process who's going to interrupt you and take over. You might be interrupted, but you are not giving up the CPU voluntarily, like using semaphore. When you are using semaphore, you give up the CPU, put yourself into the semaphore's queue. But when you are using spin lock, you are actively pulling the CPU, pulling the lock state. You're spinning on the lock state, checking whether the lock is released by another process continuously. And this costs CPU. Okay? Because spin lock and semaphore, they have many different implementations, right? But these different implementations have subtle differences among themselves. But the overall, right, the high-level difference is that the spin lock basically consumes CPU while you are checking for this lock. But semaphore means that you are going to the process is going to give up the CPU voluntarily, put itself into the semaphore queue, right, and wait for another process to signal it. Okay. Then based on this difference, can we imagine which one is better? Can you compare them? Yes.
Better for what?
For any reason that you can imagine, right? So they actually have pros and cons. Some of the one is better in some scenarios, the other is better in other scenarios for different reasons. Right? But any reason is fine. Yes.
So the critical section is very small, like if you're just implementing, that's better to use spin lock. Otherwise, you can use semaphore.
That's right, can you explain why, if the critical region is small, it's better to use spin lock?
Because the semaphore has much more overhead than the spin lock, so it's not worth opening the thread into a waiting state and then coming back doing the critical section and then.
These are all right answers. What is the overhead of semaphore? What is the overhead of a spin lock?
With the semaphore, you have to maintain like a terminal value, or like a signal for putting the thread to sleep or waking it up, and then for spin lock, it's just you have one value, say I think one only.
You're getting there, but that is not the overhead. The overhead is a context switch. Right? When you use semaphore, whenever you use a semaphore, you're going to give up the CPU, voluntarily switch yourself out. Context switch. Right? Spin lock, that's why the spin lock's cost is the constant calling, checking the lock value. Right? If the critical region is very small, it means that highly likely when you are checking, after you check for a few very short amount of time, the other process release it. Right? It's going to be found, okay, they're not going to use the lock anymore, and you can proceed. Okay? Especially in the multi-core CPU. Right? This is this spin lock. If your critical region is very small and you're using multi-core CPU, spin lock actually outperforms semaphore very often. The semaphore and the semaphore's cost is a context switch. And whenever you call wait and use semaphore, you need to voluntarily switch yourself out. And you have this context switch cost. And this context switch cost can overweigh the cost of spin lock in certain scenarios. Of course, the other way is also true, right? So in many scenarios, if the critical region is not that small, right, using spin lock directly means that you're going to waste CPU cycles on checking the lock. While using semaphore, you're not wasting the CPU cycle. Your process just gives it up, so the other process can proceed, and you save CPU cycle because of that. Right? So in other scenarios, when the critical region is not that small, spin lock often is not as good as semaphore. So because of these differences, the spin lock and semaphore, they have their pros and cons in different usage scenarios. You want to pick which one is better to use depending on your usage scenario. A similar thing happens, right? Of course, these are low-level CPU level or CPU OS level decisions, but similar analysis need to be performed when you are implementing higher level user applications. Okay. So that's spin lock and semaphore's high level difference, but we'll go through them, each of them slowly. And handling mutual exclusion is spin lock. So yeah, of course, it's used in multi-core CPU. Does not work for a single processor, because if you have a single processor and you lock it, then there's no other one that can release the lock. And a special hardware operation allows a core to test or set a special lock atomically. Right? So that's usually called test and set. Right? If the test passes, the lock is not held by anyone, then you set the lock atomically. Okay. The lock may consist of special hardware or maybe a location in memory, and the hardware guarantees that only one core will be allowed to set the lock at a time. And the mechanism is known as a spin lock because one core uses busy waiting to gain access. And busy waiting literally means that the core executes a loop that tests the spin lock repeatedly until access is granted. And this approach is known as test and set. Right? So there's often this test and set spin lock. Okay. Right. Right, so on x86, an instruction performs atomic compare and exchange. Right, so this is compare exchange, right? A special hardware instruction that compares a pair of values and exchanges them atomically. Right? And the spin loop repeats the following. Right? Place an unlocked value, right, 0 in register EX, and place a locked value 1 in register EBX, and place the address of a memory location to be used as lock in register ECX. Right? 3 registers are involved in this operation. And then execute the compare exchange instruction. Right? So register EX will contain the value of the lock before the compare, and the exchange will occur. Right? And then you continue this spin loop as long as EX contains this lock value. Okay, we have the code. Let me see. Right. Okay. So this is a code of the spin loop implementation. Right. So following this code, it might be easier. Right. So it's a spin loop. Okay. You put the EX, put the unlock value in EX. This 0 means that the lock is not locked. Okay. And you put this 1 in EBX. Right. This means that it is locked. Okay. And then this is address of the lock, right? So this ECX means that in memory you use this location in memory as a lock, okay? And then you use this compare and exchange operation on EBX and ECX, okay? EBX is a lock value. ECX is you can imagine it's the current value of the lock. Right? If they are equal, you're gonna load EBX in memory, ECX. Right? Else, you load EBX in EX. Right? Does this make sense? Right, so EBX, if they are not equal, you load EBX in EX. Right? If EX is 1, it means that the mutex was locked, so continue the spin loop. Let's go through it slowly. Right? So this else, right? Compare EBX with the memory ECX. Okay. Let's go through it slowly. Because this compare and exchange is just one of the hardware primitives people use to implement spin lock, right? So this is one version of spin lock that people implement. There are others like test and add hardware operation, and implementing locks based on those hardware operations are slightly different. Okay. Yeah. So let's give everyone like a minute. I try to understand the spin lock implementation. this is just, yeah, to understand the implementation of spin lock. Okay. All right. So we might not have time to go through this line by line because we still want to finish semaphore today. But the high level idea is that you put a value in 0 and 1 in EX, EBX. So when you do this compare and swap, right, compare and exchange, if in the end EX is 1, it means the previous value of the lock is 1. It means that it's locked. Okay, and if it's locked, then you continue. You continue the loop. You go back until you find that EX value is 0. That means the previous value of the lock was 0. Right? That's when another process has released the lock. That's high level idea of how this spin lock is implemented. But I'll leave this for you guys to read. Let's finish the semaphore today. Yeah, so this is an analog. Right? So this you're good. Yeah, you're gonna change EX value, right? So set it to be 0. Okay. Let me see. Yeah. So semaphore. Let's try to finish semaphore today so that I think your later labs will rely on this. Right. So yeah. So mutual exclusion with semaphore. Right. So you have you need to create a semaphore first, and you need to insert a call to wait before accessing a shared variable, and you need to call signal after accessing a shared variable. Right? So the protected code is called a critical region. Okay. Yeah, but this is a general principle, right? To maximize performance, you want to use the smallest possible granularity for the mutual exclusion. All right. Okay. All right. Mutual exclusion. It is needed in 2 places, in the application process, but also inside the OS. On a single process system, mutual exclusion can be guaranteed by if there is no context switch happens, which means that you can use disable interrupt to guarantee mutual exclusion. Right? A context switch can only happen when there is a device interrupt or a process calls reset. So you disable, if your process disable interrupts and it does not voluntarily call reset, then there won't be any concurrency issue. Okay. Turn off interrupts and avoid reschedule. Okay. Right. So let's let's jump ahead. We will talk about interrupt. We'll talk about the interrupt later. Yeah, so we'll talk about the interrupt with later slides that explains the how Zemu interrupts interrupt handler. Okay. This time we'll focus on semaphore. The idea of semaphore is to create an OS facility with the following properties. It permits application to define multiple independent critical sections and allow process to compete for access to these critical sections. Okay, and now the interface of semaphore. each instance of a semaphore can be created dynamically. In Xenu, you also allow dynamic allocated semaphores. And each semaphore instance is given a unique name, right? Usually a semaphore ID, okay? And each instance consists of a two tuple, right? A count and a set. Count is an integer, set is a set of processes that are waiting on that semaphore, okay? And this count is the number of processes that you allow to access the shared critical resource or shared resource concurrently. Okay, I assume that people already know this from 252. Okay, the operations for a semaphore, you can create a new semaphore, delete an existing semaphore, wait on an existing semaphore, right? And which decrements a count and adds a calling process to a set of waiting processes if the resulting count is negative. And you can signal an existing semaphore, right, which will increment the count and makes a process ready if any are waiting on the semaphore. Okay? All right. So these are the functions that Xenu invokes, Xenu designs. Right? You can create a semaphore using this initial count as a parameter. You can delete the semaphore using the semaphore ID. You can wait on the semaphore and signal that semaphore. Okay. Usages of semaphore we already explained, right? So you can use it to protect critical regions. You can also use it as a producer-consumer synchronization, like for in that I/O scenario. Okay. Let me see. Right. So this is the simplest example of using mutual exclusion semaphore for mutual exclusion. You initialize the semaphore with value 1, and you use a wait semaphore ID and signal semaphore ID to protect the critical region. Okay, but yeah, all the processes that access this critical region have to agree to use semaphores. Otherwise, you cannot create another process that does not respect this critical region. Okay. All right. One problem if you are not using semaphores correctly is a deadlock. Right? When, in this scenario, when you have two processes and you use a semaphore X and a semaphore Y to protect the modification of X and Y. Right? So there are two variables, X and Y. Right? And you use semaphore X and Y, semaphore X and semaphore Y to protect them. Okay. But a deadlock could happen in this scenario. The reason is very simple, right? So although they are protecting X and Y in the critical region, but they are ordering to obtain semaphore X and Y is reversed, right? So the process one acquires a semaphore X first, and then semaphore Y second, and then the other process acquires a semaphore Y first, and then semaphore X. Then if they execute in this order, right? So wait X, wait Y, and then wait Y, wait X, in this order, then they are enter a deadlock scenario. Okay. All right. So the solution is for deadlock. I assume that maybe in 252 you already learned some of them, right? So one is that if you ensure all the processes they will acquire and release lock in the same order, then you don't have deadlock. That's a simple solution. Others are deadlock prevention techniques involve at one time you detect whether there's a deadlock, right? By following the weight, the resource acquired relationships. Once you detect the cycle, you detect the deadlock and you break the cycle. Okay? Right, so these are techniques to avoid the deadlocks. Okay. Yeah, so the other pattern using semaphores to do producer and consumer synchronization. You have two semaphores and the control process accessing a shared buffer. The producer and consumer each operate on both semaphores but take complementary actions. Right? The producer semaphore counts the number of free slots available in the shared buffer, and the consumer semaphore counts the number of items already in the shared buffer. Right? So this is the example of producer's consumer synchronization with semaphores. I'm wondering, in 252, did you guys, I think you definitely learned the mutual exclusion, but has anyone learned how to use semaphore to do this producer-consumer synchronization? No? Okay, it's not in 252. Okay, then that's, yeah. In the lab, okay. If it's in the lab, then we'll go through this very quickly, right? So we won't dive into the detail, okay? Right. So, yeah, so create a producer and consumer semaphores before the producer and consumer process run, right? So you have two semaphores. One is the producer semaphore, the other is a consumer semaphore. The producer semaphore, right, so has used a buffer size to initialize. It means that there are this number of free slots in the semaphore, right, in the buffer. Right? And consumer initialized to be 0 means that there are 0 available items in the buffer. Okay, and the producer will wait on this producer semaphore, essentially meaning that it waits for the free slots in the buffer. Okay, it waits for the free slots in the summer, and then it will generate one item put into the buffer, and then signal, right? So the consumer, right, is telling the consumer, okay, there are more items in the buffer now. Maybe you can consume some of the items. Okay, right. And the consumer is reversed, right? So it waits on the consumer semaphore, meaning that it's waiting for the items in the buffer. And when it extracts a item from the buffer, it signals a producer semaphore, meaning that it generates an empty slot in the buffer. Okay. So in the producer, when it signals, it means that I generated one item in the buffer. This consumer, when it signals, it means that I generated a free slot in the buffer. Okay. Right, so this is the producer-consumer pattern using semaphore. Okay. Right, so this is the diagram showing how it works, but yeah, we won't dive into the detail. Okay. The semaphore emergence, right? It established a relationship between the semaphore concept and its implementation. Right? It says that a non-negative semaphore count means that the set of processes is empty. A count of negative n means that the set of n contains n waiting processes. Okay. Okay. All right. So the implementation. Okay, so this is the part that everyone hopefully need to understand in Linux, right? So how semaphore is really implemented in Linux. Okay. So if you look in Linux shortcode, if I remember correctly, there is a data structure called semtab, SEMtab. Okay. Similar to proctab for processes. You have a semtab for semaphores. Okay. And right, so the semaphores, each semaphore is one entry in that semtab. Okay. Each entry corresponds to one semaphore and contains an integer count of a semaphore, so which are the initialization value that you use to initialize this semaphore, right? And a pointer to a list of processes. Conceptually, this is very simple, right? Whenever a process waits on the semaphore, if there's no available item, right? So if the number decrements to be below 0, it means that this process need to be blocked. When it's blocked in the OS, you need to remember it somewhere, so that in the future, it need to be weakened up. So all the processes that are blocked on this semaphore will be remembered in this list that's associated with each semaphore. Okay? All right, so this list is the core, the key that you need to understand for semaphores in Xenu. Okay. The idea of semaphore is index in an array, and the policy for management of waiting process is first in, first out. But these can be changed, right? Okay. All right. Let me see. Yeah. Let's look at this implementation before we jump back to more description of the environments. So this is the semaphore implementation in this. You have a data structure called semtab. Each entry in this semtab is a semaphore. Okay, this is one entry. It has a state. Whether it's free or used. That's much simpler than process state. This just marks whether a semaphore is free or used. Okay, and the integer scount. This is the initialization value that you assign to each semaphore. And this Q, right? This is Q of the processes that are waiting on the semaphore. Okay. All right. So this is the one entry. Okay. Let me see. Okay. Do you remember where is this Q? Can you imagine where is this Q pointing to? Right? This QID 16, this SQ. Where is it pointing to? Remember, where are the lists stored in Xenu? Anyone remembers where are the lists stored in Xenu? Where? These semaphore Q in Xenu, where do they exist? Yes?
There's like a table for like the linked list of all the processes and stuff.
Exactly, right? There is a big array that's stored in Xenu that stores all the lists, all the processes, and how they are linked together. And at the end of that array, it contains pairs of list heads and tails. Okay, and this SQ, this ID here, in each semaphore, it has an ID that points to the head of a list in that big array. Okay, this is how in Xenu the semaphore queue or semaphore list, how is it implemented? You don't see the list here. You don't see the list in this entry because this QID points to a Q head in the big array in Xenu. Okay. All right. So now with this data structure, right, now we can understand how wait and signal is implemented. Right? So in wait, you give it a process called wait, and it call wait with the semaphore ID, and these are the checks. And the key is here, right? You decrement the semaphore count. If it's smaller than 0, it means that you need to block, your process needs to be blocked on this semaphore. Right? If it's not smaller than 0, go ahead. Right? So it means that you can enter this critical section. If it's smaller than 0, it means that you need to wait. Right? The current process is going to change its state to be waiting, and then see that, okay, I am blocked on this semaphore. I change its semaphore to this semaphore, and then in queue itself, into the semaphore's queue. Right? This is the semaphore's queue. It's going to in queue itself, current process ID, into this semaphore's queue. Right? And call rescan, because the current process is blocked on the semaphore, you need to rescan another process to run. And this is the core logic of wait implementation in Xenu. Okay? Now signal. We'll come back to those other slides, but now let's finish the explanation of signal. Right? Signal is also easy. Right? You have a signal with a parameter semaphore ID, and these are just checks. Right? If you increment the semaphore count and it's smaller than 0, right? Which means that you're gonna release a waiting process. Right? You need to DQ. Right? DQ remember it's first in, first out queue. So you DQ the first item from the semaphore's queue, and you call ready. Anyone remembers what ready does? Right? This will be the last question. Anyone remembers what ready does? Yes.
It sets the process state to ready and puts it on the queue.
Right? Sets it ready, put it on the ready queue, and call reschedule. Right? Call reschedule. So this is how signal wakes up the other process. Right? It wakes up the first process in the semaphore queue. Okay? So this is how semaphore is implemented in Xenu. We rushed through it, and next lecture we'll go through some of the details, but hopefully you have an understanding of how semaphore works. Okay, that's it. If you have other questions, always come up and write down the name.
If you're allowed to do anything, that's not happening.
Wait, 27 out of 30 so far. It's still okay.